Effekt, please. Immer 2 Augen überall.
Ja, das läuft.
Hast du's? Laufe, Ecke läuft. Ich laufe.
Hab's.
Gut. Wie ist es mit euch beiden da
Hab's.
drüben? Ich hab's auch, danke. Sehr gut, zweite Seite. Fangen wir die an, Ecke.
Hab's.
Vor allem der Black Magic ist wichtig, ja, super.
Die ist drauf, ne?
Ich hab's, ja.
Hab.
Sehr gut. Dann Timecode.
Got it.
Passt.
Hab's.
Hab's. Gibt's mir eine Sekunde und ich schaue, wie es mit der Box da hinten aussieht. Ah, die brauchen diese durchsichtige Box da hinten oben, sonst nur einen Boden runterstellen einfach. Perfekt.
Sonst die Sachen, die gegen die Vitrine gelehnt sind, sind wir die?
Nein.
War das da oben drauf, oder?
Wo?
Auf der Vitrine?
Was ist das?
Ja, das sind wir.
Braucht ihr das fürs Gespräch?
Ali?
Braucht ihr das fürs Gespräch? Sonst auch bitte nur runter.
Nein.
Perfekt. Das hinten kann bleiben. Ja. Clean. Yep. All good. 26 mal eingestellt, sicher. Perfekt. Für? 80.
Ja. Nur sicherheitshalber, damit ihr durchreden könnt. Da habe ich 71 Minuten. Ich muss auch Okay, dann. So.
Nicht da hinten laufen? Ja, gut.
Okay. Von mir aus
Ja, ready.
und go.
Thomas, welcome to our wonder world of minerals. And I was wondering, how is your new life as an eremit professor of the University of Bern, where you were so incredibly active, and now you're still making mineralogy?
Actually, no. Actually, no. I gave completely up continuing my original profession, and I changed my life absolutely, and I'm cleaning horse stables and I'm working with horses. This is my life, and you see it easily on the tie I'm wearing. I have no longer a tie with crystals on it.
So you're proud about your new profession?
Yes, sure.
So if you do it as good with horses as you did with minerals, then you probably must win very quickly an award in a race somewhere with the horses. I will die to watch it.
Okay.
But let's revisit together a little bit our joint past. Also, we have been working together on minerals and new minerals and fantastic stuff for a couple of decades. And I was wondering, because you were always testing students for master thesis, passing in mineralogy, crystallography, everything, whether today I can reverse it and test you.
Okay.
So I'm gonna a little bit test you out, and probably you will reverse it during the talk, and you're gonna test me later. So you know, when you think that that's too much, now I'm paying him back, then please go after me.
Okay.
Can I go after you first?
Yeah, sure.
All right. So I have all these objects here. We're gonna go and going a little bit discuss about it. It looks like a huge disaster, but there is a huge systematic in it. And after we are through with it, everybody can make his master thesis.
Okay.
Okay. So I have questions for you. If you take this in one hand and you take this in the other, something is the same and something is different.
Yes. Well, I would guess, and I only guess because without any experimental evidence, it's always dangerous to say what the minerals are, but this is probably a grossular garnet type, correct?
Spessartite.
It's a spessartite, okay. So it's still a garnet, and this one is one of this big, I would say it's an almandine, but it could also be a pyrope. It could
This
also
one
be
is a pyrope.
Okay, so it's
This is the grossularite.
Oh, it's a grossularite. Okay.
So what is the difference between this spessartite and grossolarite and almandite.
Okay.
I can put it down on the table because it's too
So
heavy.
first of all, it's very dangerous to give any secure answer on this subject. The reason is these garnets are always extremely zoned. They start with one chemistry, they change to the next chemistry, and finally the outer shape of the crystal is just a reflection of the last chemistry when the crystal grew.
Correct. So let's take what we see from outside without making an assumption on the center. That one would be unfair to test for. I agree with that one.
I would never answer this.
I agree. No, we make it that you are allowed to make general mistakes, but not major ones.
Okay.
So what would be in general, what is with the garnet groups and colors and everything? What is going on? Where we get the color from?
Well, the major reason for the different colors of the garnets is the transition metal sitting in the octahedral position. So it could be, let's say, iron, then the crystal will be black or dark.
Oh, no, that's
And if it's you said this is a pyrope,
right?
and pyrope has magnesium in this octahedral position
Exactly.
and not iron.
Right.
So you still see the pinkish touch of this crystal, and that actually indicates that it's not a pure pyrope, but it's a solid solution member between a pyrope and let's say an almandine or something.
Pearl spit, we call it.
Yes,
pearl spit.
yeah, exactly.
So it's a mixing of different garnet end members.
Yes.
And the color would not come from trace element, it will come from the
Main-
major element.
Yes.
That we call it idiochromatic.
Yes.
So
Correct.
that one would be colored by manganese.
Yes.
But probably with a little bit grossolarite component. We are leaving the garnets and you passed that first test.
Thank you.
No, but that was just the
Yeah,
beginning, it gets difficult, that
Yes.
was warm up.
Okay.
Okay, now another question. This here, I'm telling you, you take that one, and you take this one. And I'm telling you, something is the same, and something is different. Can you tell me? First of all, can you identify them?
Yeah, well, these are different titanium oxide modifications.
Right,
So this is an anatase and this is a bruchite.
exactly.
And the story behind the whole thing is that these two samples have more or less exactly the same chemical composition. They may differ in minor elements, but the crystal structure are completely different. And this has to do with the fact that the crystals formed under different conditions or different environments. So for example, for anatase, it's knowing that you have to have some sulfur in the environment that the crystal takes this modification.
Yeah,
So we
anatase
talk.
means steep angles.
Yes, exactly.
So we see these very steep, nice angles.
Yes. So the more common mineral of this group, bruchite and anatase, is actually rutile.
All right. Needles.
Needles or more stubborn crystal forms, tetragonal, heavy.
Prismatic.
Yes, exactly.
Oh, yeah,
Yeah, and
correct.
And these minerals are all fairly important if they are clear and not like
This one.
dark, like this, which is due to small concentrations of iron. And if they are clear, it's an important constituent of colors.
Oh yeah,
Titanium-
like blue anatase.
Titanium white and you can titanium white make out of anatase, and you can make titanium white out of rutile. But anatase, if you make it out of anatase, the color doesn't hold on the surface. So only the titanium made from rutile actually glues on a metal surface or on a...
So that's why all the colors are with titanium that we paint on the walls.
Yes, exactly.
Yeah. So I mean, in terms of gemology, if this one anatase we like most, the blue transparent or
Yes.
orange, and
Oh,
there are
yes.
gemstones cut blue. Unfortunately, I cannot don't have it in my collection.
Okay.
So that has a special name in mineralogy, right? When something has the same chemistry but a different crystal structure, we call
Yes.
it
modifications,
Polymorphs.
polymorphs, yes.
Right, okay. So here I have some other little tests for you. Hold that one in one hand and that one in the other hand.
Okay.
Something is similar and two things are different.
So what is, of course, both are octahedra. And that could actually be, I don't know. If it's from you, it's a diamond, of course.
Right.
If somebody else would show it, something like that, it could be everything. You know,
All right.
like that if it's
So
from you.
what is different to begin with? Same to begin with.
The outer shape of the crystal, the form of the crystal, and the difference is of course chemistry.
Yeah.
I actually don't know, is it transparent or is it
No,
just
it's not
like-
transparent.
So it's a spinel? Or?
Right, it's a spinel.
Okay, yeah.
So here, the crystal structure and the chemistry is different.
Yes,
Where the diamond is carbon,
yes,
and the spinel here then is an aluminium oxide with a lot of iron
yes.
and membrane completely black. So crystal structure and chemistry different, but the same shape.
Yes,
And the shapes, but that means we are going into having a same crystal system behind it, such as cubic.
yes.
And then the cubic like to make octahedras sometime, and then we're ending up by chance to having two octahedras. That's the same, right?
Yes.
All right, go ahead. I have to look.
I like to make an addition. If we start from the definition of a crystal is an infinite three-dimensional object. And the crystal, per definition, is not allowed to have faces. But the faces of the crystal are exactly
This one there.
those properties on which we are able to identify the crystal. Also, it's not part of the definition of the crystal. And the reason is, a crystal structure has no end. A crystal structure is an infinite thing. And as soon as you break the crystal structure, you have defects. Because the interior of a crystal looks different than the surface of the crystal. And for this reason, this is actually a reflection of the defects which we have in the structure. And the defects are characteristic of the symmetry of the crystal and so on.
You know what reminds me this? It was a philosophy of somebody only like you can bring up. First of all, it's the first time I heard it.
Okay.
But you know, you have somebody who is very similar like you, Humboldt. Because he met with Goethe and at that time and created what is nature.
Yes.
And that also have all these philosophies inside and everything. And then out of understanding from material and study everything comes a greater understanding of the world, whether it's in organic or inorganic. So it's such a pleasure to make this experience here with you. We will be unique, yes, right? So I very much appreciate, but it's not the end of the test.
Okay.
So we are gonna looking this here. 1, 2, and let me see which one, and this one.
Yeah.
This belong together, and this one. So there is a very unique story and beauty story in this.
Yeah.
Something is all same, and something else is different.
Yes.
It's your turn again.
Okay.
If you want to pass the test.
Yes.
Give you 90 scores, it's okay. But we're probably gonna make 100 total, you know.
Okay.
All right.
So first of all, from a mineralogical point of view, these 4 specimens belong to the same mineral species. The species is beryl.
Correct.
And all the varieties in color which we observe here, the green coming from the chromium, the blue coming from the iron, or the pinkish color, which is actually mainly caused by 3-valent manganese, traces of 3-valent manganese. So we call this different color varieties, and so this would be called aquamarine or something like that. This is a typical, probably even Colombian type, or
Correct. What? Emerald.
emerald, yes. And this one is probably a morganite,
Correct.
a pinkish type of beryl. It could be also something else, like a pezzottite or something like that. But the only reason that I can say it's probably not a pezzottite, because even you could not afford a pezzottite of this size.
How do you know?
I don't know. Simple assumption, simple assumption.
Right. We leave it.
I have never seen such a large pezzottite.
Actually, when I got it, I hoped it's a pezzottite.
Yes.
And then I tested its cesium concentration, and it was just at the border and not
Yes,
one. And I
yes.
was like, no way.
Is it from Afghanistan?
No, the same like where the pezzottite
Okay.
come from, the same mine.
Okay.
It is so sad.
Yeah.
So what was the difference between this and pezzottite? Actually, we did publish it.
Yes.
Right.
So the major difference is the chemistry
Together.
Yes.
Right.
Yes. The chemistry of the pezzottite is much more complex. So a normal beryl has no lithium in the structure, or let's say not significant concentrations of lithium. And the other thing is the beryl structure has always these open channels, and these open channels may carry sodium, potassium, water, and in the special case of pezzottite, you have extremely high cesium concentrations, and cesium is a large ions which plugs the channels in this structure, exactly. So for this reason, the cesium leads to some specific ordering patterns in the structure, which means it no longer follows the classical hexagonal structure of, let's say, the morganite with more or less exactly the same color, but it reduces the symmetry, it becomes rhombohedral, and the cell is much larger than the unit cell of a common, let's say, beryl type mineral.
Superstructure.
Yes. So you're absolutely right, the basic structure, if you just look at it, a fast glance on it, then you think, oh, it's the same as a beryl. But if you look at more detail, then you see, oh, there's some ordering pattern between the lithium and the cesium in different positions in the structure, which reduces the symmetry and is unique for the pezzottite.
Can I tell a little story?
Yes.
Because that was just perfect summary, but there is a little event behind it, right?
Yeah.
So this crystal here, there were 3 groups working on it
Yes.
to identify the mineral.
Yes.
And then they joined from California University and American institution and so on, because nobody knew what it is when it first came, because they have a higher refractive index than beryl.
Yes.
They didn't know what to do. So it was the hunt out who can determine this crystal structure.
Yes.
I take a piece off and went to you in Bern, and there was this huge machine with multi-channel detector X-ray thing that you had for zeolite research, got sponsored from, I guess, the oil industry or something, or from university. And then you were working there, and I came, and then you joined me and measured this, and then how long did you take you to measure that crystal structure?
I forget.
I know. Almost a month.
Yeah,
because it had the superstructure has so weak peaks you couldn't get it out quickly.
Yes.
The others didn't have it.
Yes.
So they were getting necessity to join with us.
Yes.
So that's why we gave this mineral later with the chemical formula of cesium, beryllium, lithium, aluminium silicate, the space group R3C and everything, and applied to the National Mineralogical Association for a new mineral, together with a group from Caltech University and so on. Everybody joined with Professor Hawthorne, is in your league and so on, and we applied it and got the name pezzottite for him. So we discovered the new mineral, right?
Yeah, correct.
So I decided to make this book as a cooking book, how to make a new mineral.
Yes.
Step 1, step 2, step 3, because I was like, if somebody else wants to go through the same suffering like we went, they need a cooking book. And I found out that the references is everywhere in the world as how to make a new mineral. Yeah, and that was the name of our article, The Challenge of the Identification of a New Mineral Species, example Bezotite. And
Yes.
all the steps, exactly how we applied it to the IMA, I followed up and showed how we did it, how it is happening, and what you have to do so you can get all these different things out that you need to make a new mineral, right? And then we have all the machines from everything was necessary. We had the chemical analysis with electron microprobe and laser ablation, and we had yours with the crystallography study, and we had to all put together. Then you have to compare it to all the other minerals existing in the world, right? And then with the bezotite crystals and everything, and what is different than the others, and all that, and we applied, and it got approved.
Yes.
Wasn't that crazy?
Yeah, absolutely.
Absolutely crazy.
Absolutely.
And then we were like with the top mineralogists together, everybody together made it, because we joined in relatively late.
Yes, yes.
But you had that absolutely fantastic edge of the knowledge machine that was multi-channel and showed all the reflection of the crystal structure like a sky. And you can run it forever, and you got the weak peak out from the superstructure, and then you solved it.
Yeah, yeah.
Right? And to make a new mineral, you need the space group.
Yes.
And only our group
Yes.
could do it.
Yeah.
We were the one.
Yeah, yeah.
I don't say the others were wrong, I
No,
just
no,
say
no,
we
no.
were the one.
Yeah,
But they
yeah, yeah.
needed us, and so we did that. That was quite interesting.
There is a funny story in the background.
Oh. I never heard it.
Probably not. Probably not.
Uh-huh.
We actually have solved the structure of this mineral bezotite, showing the lower symmetry, showing the distribution of cesium and lithium in the structure and so on. But I was never 100% content with the quality of the data I collected on this crystal. As you said, I had to collect the data for months to see the very weak reflections.
I remember very well.
And then, of course, the quality of these weak reflections was not so excellent that we could determine the thermal motion of these positions of the lithium and so on. So I was not so happy with it. I could publish, let's say, the outer shape of the structure, but I was not willing to publish the numeric values of all the coordinates
Or the position of every atom.
position of every atom. I could have done it, but I was not happy because sometimes there were inconsistencies about the thermal motion of the atom. So I said, okay, the quality is not good enough. I can do it later, measuring half a year when I have a machine available or something like that. So then finally, somebody noticed, oh, the structure has not been published yet in details with all the coordinates.
Blood droplet.
Yes, and they published a structure in a quality which was less than 10% of the quality of a structure I had on my desk.
And you didn't publish it.
No.
These are is this one of the regrets in life?
No.
It's just science.
No, it
happens.
Yes.
Yeah. I have also a lot of these files
Yeah, sure.
that somebody else, I found out, and a half year later somebody published
Sure,
it.
sure.
Sometimes it makes like this.
No.
Somebody else found it out. No?
No.
All right.
Of course, if I would had to review that paper, which I had never the opportunity to do,
You would have found it out.
I would have said no. This is not the quality you can publish in an international scientific journal.
Oh.
But okay, that's it.
Now I know more about it.
Yeah.
Okay, it gets heavy lifting now. We change the topic.
Okay.
Hold it.
Okay.
How heavy is it?
Let's say it's very heavy.
No, kilo, 2, 3, 4.
I would say 3 kilo.
Yeah. All right. That would be like 150,000 carats or something.
Yes.
Like 15,000, right?
So it's an epidote.
No.
Okay, then
Look
it's,
at here.
yeah, okay. No. Then it's a tourmaline, a shearl, a black.
Yes, exactly.
Black tourmaline.
So that was just an introduction into the tourmalines, and then I give you something else, and then you notice a little difference.
Yes.
What?
Expansive color of tourmaline.
Remember the name? that's unfair. It's a gemological background.
Yes.
I cannot test. It's a Paraíba tourmaline from Brazil.
Yeah, Paraíba. Yes, I remember the name.
So
yes.
how is it colored? Which element? That one counts for passing the exam. Remember the cop? Oh, I gave you already the answer.
It could be copper.
If
it's
100%.
Yeah, okay.
Yeah, and the general type of tourmaline, because we have tourmaline is a group,
Yes.
and we have minerals inside the group.
Yes.
Do you remember a few of them?
Most common elbite, dravite, and so on. Yes.
Yeah, elbite, dravite, lidicoatite, and so on. I mean, sometimes we look tourmaline when we cut them through, right?
Yes.
And then we see that they are zoned. You said it already for the garnet that is zoned.
Yes.
And here, you see this?
Beautiful.
This is one crystal we cut, tak, 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 tak,
Yes.
and this is the center.
Yes.
So what you guess is the chemicals change in tourmaline inside the crystal? What would be here? What elements could we expect? It's a guesswork, but speculation. But
yes,
can do it.
I would immediately say it starts like an elbite with lithium and manganese 3+, giving the pink color, and then the iron increases, and then you get the greenish parts of.
And lidicoatite.
Yeah, could always be, but
Yeah,
you cannot.
Yeah. So elbite, dravite, lidicoatite, rosmanite,
Yes.
all these are singular minerals that
Yes.
are considered as end members.
Yes.
And all of them have different qualities and so on. And so it's so difficult to say. So we say only the group, right? Okay, so fine. Well, this is just to sum up that sometimes the elbite
Yes.
make some magical little
Yes,
mineral
yes.
specimens, huh?
It's certainly not from Elba.
No,
No, this quality you don't find at Elba.
yeah. It's from Africa.
Yes.
Okay, you get it all right. I can't teach you anything anymore. Okay, so I take these two things here to you. This one, look at
Okay.
the transmission, and look
Yes.
at that. Something is same, something is different. You
Yes.
want to a little bit talk about it?
We only have 22 seconds, so I think I need more time to explain the details. Of
Okay,
the
so
two
we're
things.
making a cut here.
Ich laufe.
Black Magic läuft.
Danke.
Don läuft.
Nur auf den Timecode. Was?
Hab ich?
Hast du?
Ja, hab ich auch.
Ja.
Habe ich auch. Dankeschön.
Wunderbar.
Lichter sind wieder überall an.
An bzw. überall, wo sie nicht sein sollen, aus.
Yep.
Gut.
Tschüss zu.
Tschüss zu, ja.
Dann lassen wir den Hammer noch darüber und dann.
Geht schon los.
Thomas, another test.
Okay.
A lot is similar, but something is different.
Yes.
It's a bit heavy, so I'll
Doesn't
be
matter.
make
Yeah, sure. Let me tell you first another confusing things which students normally mix up. The greenish stuff which you see here and the concretion of green, these crystals here, belong to the group of olivine.
correct.
In gemology, you call them
Forsterite violet.
no
Yes.
peridot.
Peridot. Gemology, yeah, peridot.
Peridot.
Peridot, yes.
The large group of these olivines, well, let's say the most important members of these large groups is the magnesium member, forsterite, and the iron member, phyolite. And forsterite and phyolite form a solid solution, and probably both of those are members of a solid solution. And this one, as you can easily see, is from a meteorite. And the formation conditions of the olivine in a meteorite is completely different to the ones in a basalt, as we have here.
How much
And-
temperature?
Well, it could be basalts 900 degrees, 1000 degrees.
1200.
Yes, yes.
Alright. And this one? formed at the collision of planets in the asteroid belt?
Yeah, come on. Let's say considerably higher.
All right.
Okay.
Right.
So the solid solution is of course different between these two, and
But something we can say, something it's not.
the crystal structure is more or less the same.
No, but something it's not. Forsterite.
Oh yeah, sure.
Forsterite is white.
Yeah, sure.
It does not call it. So it's not forsterite.
Yes.
Both have a component of firelight.
Yes, but almost all. I think there are some olivines from the Black Sea areas. These are the purest forsterites, I guess, on the world.
We have them here.
Okay, okay.
White forsterite.
White forsterite.
veins, but also crystal.
Yes,
also facet
absolutely,
them.
absolutely.
Yeah.
But all the other ones are always limited solid solution members between forsterite and firite.
What would you expect as a trace element to be different between this and this? Expect.
Of course, meteorites have different manganese concentrations, higher manganese
Or if
concentrations.
you consider the matrix, what would be the matrix of a meteorite consisted of?
Iron,
And
nickel.
exactly.
Yeah, yeah.
Right. So can olivine theoretically have some nickel in it?
Oh yeah. There is synthetic nickel end member olivine.
Yes. So that us as gemologists, we distinguish then one from the Earth and one from the planet by the nickel concentrations and slightly
Yes.
different
Yes.
ratio.
Yes.
So you just invented a new test.
Okay.
All right. So okay, we let that pass for you. Can you tell me what is this? It's not really fair, but you know, sometimes life has to be difficult. If it's only easy, we fly too fast, too much. So another one of this. It has to do with this. I help you.
Okay. But you don't want to tell me that these are also olivines.
They are,
Okay.
but they are formed hydrothermally in Mogok.
Okay.
So,
Okay.
so this one is a basalt, this one is asteroid, and this one is in the metamorphic hydrothermal veins inside peritatites. And from this we cut as gemologists or in the gem industry the very valuable peridot crystals.
Okay.
Again,
Okay.
now sometimes I can teach you also.
Yeah. Sure.
Alright.
Sure.
Forgive me.
Do you sell also peridots as gemstones coming from the Eiffel district?
Sell. I
Yeah.
don't sell, I test.
I test, of course.
Test. No, you please bring me. I don't have it.
Okay.
All right, bring me that. Look, something I'll tell you. You told me that you are only interested in horses anymore. I don't believe you. You know why? You have here a symbol of a crystal on your jacket. So you took a tie and this one. And if I'm not mistaken, this is an award from the Russian Academy of Science.
No, but it's appetite.
An appetite crystal structure. Because I witnessed you get like the highest awards in the world of mineralogy from the Russian Academy of Science. First one?
No.
Which one was it? I witnessed it during your...
Yeah. No. I'm a honorary member of the Russian Mineralogical Association.
Yeah, that's what I see. They made you an honorary member. The Russians know how to check crystal structure and everything, and so that is. It's not easy to get that one.
Yeah.
I know that one. Okay, one thing I wanted to show you, also quite impressive and important also for gemology is these two. One is, as you see, the color right, red. I don't have to ask you, it's easy, and this one is blue, and they have.
I have to guess again. No.
Yeah.
I would say if you show me that, it's probably a cobalt spinel
From Vietnam.
from Vietnam, and this is a classical red
Chromium.
spinel it comes from chromium, and it's surprising again because we were having the barrels and we had the chromium color making the crystals green.
And this one?
And this one is red.
From chromium. One time it makes green, one time it makes red.
Yes, exactly.
Why?
It's the environment, it's the crystal field environment of the crystal structure which is responsible that the chromium has different transitions, and so it can be responsible for the greenish color. And as in the rubies, this is almost ruby similar color, right?
Yeah, yeah.
So it can also make crystals red.
Oh, yeah. So if somebody says chromium makes red, it's wrong.
It's wrong. Yes.
Yeah. So we make this as a landmark statement.
All these statements are more or less wrong. For example, cordierite, as an example, you call it also as a gemstone iolite,
yeah.
because it's ion.
Used by the Vikings.
The violet, yes. Yes.
To navigate the stars.
Exactly.
Why? How did they do it? Why did the Vikings use cordierite, iolite to navigate the north?
Well, it's the extremely strong pleochroism of the crystals, which is color dependent, which is direction dependent, and it depends on the polarization of the light. And so you can actually determine whether you have light coming from the north or you have
They looked with the iolite,
yes,
and when there is a lot of light,
yes.
they see dichroism. When there is less light, they see less dichroism, so they could find out in the foggy north where the sun is.
Yes, yes.
And then they knew with the time and the place of the sun,
Yes.
they could navigate.
Yeah. Yeah.
And they needed the iolite for that.
Yes.
And that was their secret
Yes.
trick. That was the enigma machine of the Second World War, was the iolite of the Vikings. And we could have invented it with our knowledge.
Yeah.
Right?
Sure.
All right.
Yeah. But let me just come back to the color problem again. We were talking about the cordierite, because iolite, it's bluish, lilac, bluish, and so on. It's two-valent iron. Two-valent iron is also responsible for the green color in the olivine, and two-valent iron is for the baby blue color
In the aquamarine.
in the aquamarine.
Yeah.
So actually, the color alone is extremely dangerous for determining what kind of element is it. Yes.
Besides that, we have idiochromatic and
Yes.
allochromatic with major element and trace elements, and then
Exactly.
we can have both
Yes.
allochromatic and idichromatic and put in traces, and then we can think this is a general mineral formula. Call it, actually have also traces in it,
Yes.
making it so it's all open. That's why we needed to go also together, away from all this thing, into more deep analysis. And there was this one mineral
Yes.
which I sent
Carries your name. Carries your name.
right, and I sent it to you. I wrote
Yes.
new mineral on it,
Yes.
and it was in one of these crystals, right?
Yes.
So now you tell me the story, because after I sent it to you, it was taken out of my hand soon, and they say, get it.
Yes.
Now we are doing the job.
Yes. Exactly. Exactly. So first of all, I should mention I received during my active time, let's say 20 minerals per month and people were saying, oh, it's something new. You have to look at it in more detail. And we put it on our machines, and it was well-known material.
Aragonite, calcite.
Boring. Or even synthetic stuff, and so on. So you sent me this crystal, and these were yellow needles enclosed in this phenakite. Phenakite is a beryllium silicate occurring in pegmatitic rocks. We should probably shortly mention what a pegmatite is. Pegmatite, the melt of a pegmatite is the relict melt which doesn't fit into the chemistry of a granite.
Yeah.
And
A melted body
of
down in the earth,
exactly.
and everything crystallizes,
Yes.
and something doesn't know where to go,
It doesn't fit into the
and it
granite.
makes a last run, and then makes an emergency crystallization and try to find out what the hell we're gonna do now with the remaining
Exactly.
incompatible elements like lithium, borium, everything that doesn't fit in
It costs a
quartz
lot
and
of money,
everything.
yes.
And that one makes us the gems, right?
Yep.
Yeah. Okay, so we are there now in that system.
Yes.
Here it is, by the way.
Yes.
And here's the phenakite, the quartz, and here
Yes.
is the pegmatite.
Feldspar,
Right?
yeah.
Oh, yeah.
Okay. And yes, so we looked at the crystals. They were maximum length of 2 millimeters, about diameter about
Half
well,
less.
less. I would say less. And we analyzed it, put it on the machine.
So analyze mean you break it out first.
We break it out first.
And you
yes.
get one of these small crystals
Some
out. Which is
extreme-
not easy, no?
Yeah, I know, but you can actually crush the whole phenakite, and then you have tiny fractures of this yellow material.
A thousandth of a gram.
Yes,
Mhm.
yes. And the size of the crystal we put on the machine was about 0.1 millimeter in
100
maximum
micron.
dimension, 100 micron in maximum dimension. And then we measured it, and we found an extremely confusing diffraction pattern. So diffraction means if you shoot with an X-ray beam on a crystal, then you get the so-called diffraction phenomenon, and you get this picture with the different points. With these different points on it, we analyze.
Looks like the sky, the
Yes.
galaxy.
Yes, but it has symmetry.
Asymmetry.
Yes, this is the important thing.
Yeah.
Because we cannot live in crystallography
So that is
without the
these are
symmetry.
stars made by peridotite.
Yes, exactly. So from this on, we had to assume that the crystal is actually tetragonal.
Like four.
Yes,
four-
it has a
four symmetry.
yes, rotation axis in it. But then we looked at it under the polarizing microscope. Do we have also the picture of the polarizing pattern?
So, wir müssen den gerade machen. Warum?
Sorry.
Yep.
Ali, du hast das vor das Mikro gehalten jetzt die ganze Zeit. Ich habe dich nicht mehr gehört.
Okay.
Warte, ein Stück.
Ja,
Er tauscht
sorry.
einen Akku.
Hast du gecuttet?
Ja,
Ja.
wir müssen gerade.
Laufen?
Yes.
Ja, warte, Hannes, warte.
Und
Läuft's, ja?
Hab's.
Kannst du das mir ein bisschen höher heben, bitte?
Ja, natürlich.
Hab's.
Ja.
Dankeschön.
Ich versag's dir, das Mikrofon ist böse.
Joking.
I know. Me too.
So more.
Ready?
Ja, also bei mir passt.
Okay, and go.
You were saying?
The important thing was that we first thought that the crystal has tetragonal symmetry, which means it has a fourfold axis, a 90 degrees rotation repetition in the structure.
4 times 90 is 360.
Yes. And then we could not solve the structure, which was very strange because the quality of the crystal was actually excellent.
You mean like the chemistry and the structure would not make sense when they were mixed together on the wrong premise that it is tetragonal?
No, we could not refine a tetragonal structure with it.
Ah,
The diffraction pattern was showing the fourfold symmetry, but when we were doing extracting the atomic positions, then we received nonsense. Two short distances, it made no sense at all. And then we said, oh, we have to look on the crystal in a specific direction along the fourfold axis. And then we did this on the polarizing microscope, and then we obtained this funny picture. We would expect normally that we have a clear picture, not this sector, not these sectorings. We call it a sand hour phenomenon, what we observe here. And that is typical for an integral twin.
An aggregate.
Actually, an aggregate of several individual crystals grown together. And then we said, okay, the symmetry must be lower, and then we did several tests, and then we came out with a twin model that the crystal was originally not tetragonal, but orthorhombic, and what we observed at the beginning was actually an overlay of two different patterns which were simulating the roll symmetry.
Due to tilt
Yes.
systematic tilt
Yes.
of the different
Yes.
partners of aggregates involved
Exactly.
in the mosaic structure.
Exactly.
So tetragonal would be one 4-axis
Yes.
and mirror perpendicular
Yes.
it, and orthorhombic would be one mirroring and the second one to it.
Yes. So
Without the four-fold, only two
two
folds,
fold axis.
this way
Exactly.
and this way.
Yes. Okay. So this was one of the major problems. Nevertheless, we recognized it's something completely new. We have never seen a structure like this, which we could solve now with very high accuracy. And then we contacted you and told you it's new. You're out of the business. We do the job. But why has he to be out of the business? Because if you define a mineral with your name, you cannot publish it. Always other people have to publish it. So for this reason,
Dependency.
yes, for this reason you were out of the
All
game.
my contribution to the chemistry and
No.
that has yttrium
No.
and found and this and that, everything I had to trash.
Yes, exactly. Nevertheless, the crystals were beautiful, extremely large for new mineral, because I remember the old story of my former colleague Ernst Nickli at the University of Bern. He said, if you name a mineral after me, I want to be able to stand on it. And they finally named a mineral after him. It was only found once at the Bintal Valley mine, and the mineral is about 10 micron of size.
So they didn't follow him.
Yes.
Obviously.
Yes, yes. So this one is actually for new mineral. This is a huge thing. Then the other interesting thing is it's not only a new mineral, it's new in chemistry and new in structure. Very often a new mineral or a new mineral species is just a repetition of something else which already existed with a slightly modified chemical composition. But this is not the case here. This is structure new, chemistry highly unusual, complex and new. So we took together a big group actually from colleagues in Japan, in Austria, people in Switzerland and so on. Everybody collected a small part of the properties of this material, and then we put everything together in minimum time, maximum output in minimum time. And
6 months, right?
Yes, I would say after 6 months the mineral was defined. The application to the IMA, International Mineralogical Association, Commission on New Minerals and Mineral Names, was written and approved, and then we submitted the paper. It was after about 20 days already reviewed and accepted, and so for me this was a world record. I have published
You said
already.
that was a world record of making new mineral. That's
Yes,
what you told me
yes,
last time.
yes, exactly.
And then you wanted to have a party for that.
Yes,
And
this
I
was
made
my
a
requirement.
huge
Yes.
party
Yes.
down at the Lake of Luzernwitz
Yes.
now. A
Yes.
huge party.
Yes, that was
With the
marvelous.
boat, and it was marvelous.
Marvelous,
Yes.
marvelous.
Yeah, unbelievable. I remember. We have all the details recorded.
Okay.
I've found that mineral in Mogok, and my idea was phenakite is rare.
Yes.
And I had 20,000, 30,000 of them, the entire production from Momek, about 45 kilometers away from Mogok. And I brought it to the market. And I was like, if I am looking into a rare mineral, and inside a rare mineral,
Yeah.
I found a rare inclusion, it must be new because it's not easy to do that.
Yes.
So 20,000 times 5 minutes.
Yes.
100,000 minutes of searching.
Yes.
And then it popped up in my front of my head like these ice pickles.
Yes.
And I was like, if this is not a new mineral with this shape I've never seen, I've seen so many minerals everywhere and do nothing else in my life. If this is not a mineral, I don't know what that is.
Yeah.
Right?
Yeah. There is a second aspect to be talked about. Probably the only reason why peritite still exists today is because it's enclosed in the phenakite. the phenakite has protected the material from
overlooking
corrosion, from corrosion, from decay under varying environmental conditions and so on. So what we have here is
We know the
something.
ages is 23 million years
Yes.
old, by the way, we measured the
Yeah,
zircons,
yeah,
right?
yes.
23 million years old
Yes.
is very, yeah.
Amazing.
Amazing, huh?
And it's contained, let's say, like a sailing boat as a model in a glass bottle. So your peritite is preserved in the phenakite for how many million years?
23.
23 million years.
And we have these different elements, all the rarest elements, samarium, gadolinium, dysprosium, terbium, holmium, erbium, and yttrium, lutetium. All these rarest elements, we have them in almost percentages and or tens of or half of percentages, very unusual.
Yes.
And then we have at the same time light elements, beryllium and boron. And then we have the yttrium. And then when you look all this chemical inside, you think how they were formed. And then you find out that some were formed by giant supernova explosions, like the heavy ones. And then the light ones like gamma rays and so on, where lithium and boron beryllium is. And that all had to come from space somehow on planet Earth.
Mm-hmm.
It had to move with plates down and mixed into a granite, melted up. And this little bit has to come up with a pegmatite. And it had to not place anywhere else. And it created a little structure from emergency and formed it.
Mm-hmm.
And when you put all this new mineral into one little a bottle, it's not bigger than this.
Yeah.
And sometimes you rescue a formula and chemistry for the world, right? And it's a good feeling.
Yeah. Oh yeah. And all the members of the group which were working on it were also extremely proud to have contributed to this finding of such an extraordinary new mineral. And you mentioned before, we have seen in the literature, peritite is now no longer a standalone mineral, but they have found in the former Soviet Union, Pamir Mountains.
Kazakhstan.
Yes, they have found another chemical variety of it. I think it's more rich in beryllium.
Right, in place in boron.
Yes, and in this mineral here from
Kazakhstan.
no, from the original
Momek.
locality, yes,
Momek Murma.
has less beryllium, but
Also traces.
higher boron concentrations and so on. But
So they found another end member of it.
yes,
And they called
yes.
it Badakhshanite.
Oh, I can't. Yes.
Badakhshanite.
Yeah. Okay.
And then it's now the peritite group minerals.
Yes.
So a whole group of minerals get the name. That makes me proud.
Okay.
No, that's what happens in life.
You're no longer as member of a standalone mineral, but you're a father of a group.
All that happens in life
Yes.
sometimes. I summarize very quickly what we found. We found beryl group minerals that are formed, have different colors due to different trace elements. Emerald, aquamarine, morganite, this manganese, this iron, this chromium as trace elements in the matrix. We found garnets, grossolite garnets, almandite garnet, and spessartite garnets, who are major elements, and they form and mix together and forming all these different garnet group minerals, which contain end member minerals that were named, as we said. And we have seen that if the morganite increases in calcium concentrations, it creates a new superstructure, which is pezotite. And then we have seen that minerals can have the same chemistry but totally different shape. We call it polymorphy. And we have at the same time see that the tourmalines belong to the tourmaline group, but they contain so many different minerals that are named after Rosman, Rosmanite, lidicotite, then after the island of Elba, Elbite, and as more, and dravite and schorl, and they're all mixing together, which we see here in one crystal when it grows from the center to the rim. We see all these end member of tourmalines. We have seen that that the painite, we didn't talk about it. We have all the borate minerals that we work together and we made discoveries and so on. Also the yokakidolite and so on. We had not only one mineral made, we made several together. And we ended up with specialities and little anecdotes. We have seen in the peridot that the peridot or olivine is formed, depending where it's formed in the world, in an asteroid belt or in a volcanic rock, that they are almost similar but not exactly, and have different trace elements and are almost mixed between two end members. So it's a lot of story behind everything what we're doing, and I want to end up this with the last question for you. What is this?
Oh, this is a beautiful Japanese quartz twin.
Right. So something like this we also found in Mogok. And that is like the dream to have it. So sometimes crystals also join together and form completely new things.
Yes.
And so it's a nice symbol for our cooperation.
As the peritite, which is also a twin.
And here it is.
Here it's and here it's microscopically visible. You know.
So I want this to be the symbol of our cooperation,
Yes.
the Japanese twin quartz.
Yes.
And keep it here and cherish it as a symbol of that. You agree on that?
Yes. Nice.
Perfect. Thank you so much for this going back, and we can smile with the camera together.
Ja, machen wir noch kurz einen Cut?
Ja.
Cut, good.
Genau.
Das ist noch nicht blau.
Ja, ja. Also nicht, zweiter, vierter drauf gestanden. Oder falsch gesehen? Das ist fertig. Gibt das ja? Das ist schon cool. Ich mache ein Hobby, das machen wir voll. Okay. Ja. Also ich meine, was gerne macht. So, ich auch früher. Gegen Milch, gegen Fleisch, am Fell, das ist irgendwie so das ultimative Kosten. Ich finde, das sind die coolsten Viecher. Ist unser Spiegelung drin oder irgendwas gedacht?
Toll.
Alles schön,
Ja, gerne.
Wenn wir irgendwo anfassen.
Ja, ich will nur zuerst mal probieren. Wie lässt man die Luft wieder raus? Achso, okay, dann weiß ich, wie es funktioniert. Also
Zumindest der Quetschung, die jede Woche behandelt wird.
das geht gut. Das kann man problemlos dann machen.
Man muss nur oben drüber kommen.
Ohne dass man so schummelig. Wollen wir es gleich machen?
Geht das?
Am besten hinten jemand, damit es nicht so wackelt. Ja.
Magst du das und ich krieg deine Pizza?
Okay.
Dazu wahrscheinlich.
Welche ist jetzt da?
Den muss man interpretieren. Hör?
Ich weiß nicht. Vielleicht deine.
Das war alles gut.